For more information, please visit SGMAK Associates website.
Let us talk about use of binomial distribution. We use binomial distribution when you are interested to find out the probability of k success in n independent Bernoulli trials. By definition, a Bernoulli trial generates two outcomes only. We define one of them as success, depending on the application, and the complementary outcome is defined as a failure. For example, the number of heads in 5 independent toss of a biased coin can be solved using binomial distribution. If you assume that the biased coin has a probability of getting a head 0.7 is biased, so the complementary outcome tail, probability of getting a tail is 0.3, then you can estimate probability of exactly getting 3 heads in 5 trials by using the binomial mass function, binomial probability mass function, given by combination of 3 out of 5, 0.7 raised to the power 3, and 1 minus 0.7 raised to the power 2, which is 0.309. Now in this example, the outcome head is defined as success with probability 0.7 in each trial. Each trial is a Bernoulli trial. Probability of getting a head is 0.7, getting a tail is 0.3. Remember, in solving a problem using binomial distribution, the user has to define the success, and it is problem specific. Now, two other events that may be of interest are probability of getting 3 or less heads in 5 trials, and probability of getting more than 3 heads in 3 trials. So we're defining two events here. What's the probability you get 3 or less number of heads in 5 independent trials, and 3 or more than 3 heads in 5 trials? Now, the probability mass function for binomial distribution is given by probability. The random variable takes a value k, is combination of k out of n, p raised to the power k, and 1 minus p raised to the power n minus k. The distribution has two parameters. One is n, which is the number of independent trials. Another parameter is small p, which is typically represented in most of the textbooks. Small p represents the probability of success in each trial. So probability x equals k, given by a combination of k out of n, small p raised to the power k, 1 minus p raised to the power n minus k. So probability of getting 3 or less heads will be probability of getting 0 head, exactly 1 head, exactly 2 heads, and exactly 3 heads. If you all add them together, that probability for that event comes out to be 0.471. So if you take the complement of that, probability of getting more than 3 heads will be 0.529. Take another example. We are looking at a manufacturing process that generates on average 100% defective parts. So on average, every 100 parts, it generates 1 is defective. Now we take a random sample of 6 parts from the process and carry out 100% inspection. So we take a random sample of 6 parts and inspect each one of them. And inspection of each part is a Bernoulli trial. We define success as getting a defective part. Remember, definition of success is problem specific. So probability of getting a defective part in each trial is 0.01 because the process generates 1% defective parts. So we want to estimate the following probability of the following events for the sample. We get no defective, a sample of size 6, one or less defective, or we get all defectives. So once again, we have taken a random sample of 6 parts from a process that generates on average 1% defective. We are doing 100% inspection of the sample, and we want to find out the probability of the 3 events that you have defined. Probability you have no defective in the sample, one or less defective in the sample, and all the parts are defective in the sample. So let's estimate those. Again, remember we define, in this case, success as when the inspection process. Now we have already described the parameter of binomial distribution, which is n and p, number of trials, and p stands for probability of success in each trial. The mean for the random variable is given by n times p, and the variance is given by n times p times 1 minus p. So if I use the PMF, probability mass function, and for this particular problem n is 6, we got sample of size 6, so inspecting the entire sample means carrying out 6 independent Bernoulli trial, and p is 0.01, 1% defective. So you get the following results. Getting no defective in the sample, probability of getting no defective is 0.941, one or less defective is 0.998, and probability of getting exactly one defective is 0.057, and probability of getting all defectives is 10 raised to the power minus 12, which is almost 0. We can use a statistical function provided by Excel to estimate probability from a binomial distribution. We use the following function, binomial binom.dist for binomial distribution, and that function has 4 arguments: number of success that you're interested in, trials, probability underscore success, cumulative. And let me explain. So binomial distribution in Excel requires 4 inputs. Number underscore s represent number of success we are interested in. Trials represent how many Bernoulli trial we are performing, carrying out. Probability underscore s represent probability of success in each trial. Now cumulative has an interesting meaning in Excel. If you make it true, then it represents cumulative probability. If you set that as false, then it gives you the probability for a respective value. Once again, if we set the 4th field cumulative as true, then you are getting the cumulative probability. If you set that as false, then you get the probability for a specific value of the random variable. So if we going back to the previous example, the probability x less equal 1, that means we have 1 or less defective in the sample of size 6. So we'll use the binomial distribution. We'll put the first field as 1 because we are interested in 1 success, though it's 1 or less, we're coming to that. 6 independent trial, value for the parameter p is 0.01. By setting the 4th field as true, you are finding the cumulative probability for 1 or less number of defectives. So in this case, we are really summing up probability of 2 events. Probability of number of defective equals 0 plus probability number of defective equals 1. And Excel returns a value 0.998. Now if we set the 4th field as false, then as you can see here, we are putting in binomial distribution parameters 1, 6, 0.01, and the 4th field you are putting false, we get a value 0.057. This represents the probability of getting exactly 1 defective in a sample of size 6, where the probability of success in each trial is 0.01. So use binomial distribution to calculate the probability of k success in n Bernoulli trials. Well, probability of success in each trial is a known constant. and a success is defined by the user.
For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website.